So oxidation of alcohols. Oxidation, I hope you remember from the organic definition, is often making bonds to oxygen. 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 Let's try that again. We could also say it's breaking bonds to hydrogen, but making bonds to oxygen is an oxidation reaction. So these things on my reaction arrows are oxidizing agents. Oxidizing agents help other things be oxidized. So those oxidizing agents themselves get reduced. That's an old Gen Chem thing. I hope you remember that. So this alcohol can be oxidized. If we make a new carbon-oxygen bond, that classifies as making bonds to oxygen. If we make a new carbon-oxygen bond, we're also going to break this carbon-hydrogen bond and that oxygen-hydrogen bond at the same time, well, in the same process, to get this thing. This thing is a ketone. That alcohol has been oxidized to a ketone. This alcohol can be oxidized to make a ketone. This alcohol can be oxidized to make a ketone. Yeah? All of these alcohols are secondary alcohols. That secondary is important. Secondary alcohols are oxidized to ketones. That's no exceptions. Secondary alcohols are oxidized to ketones. The common thing about all of these oxidizing agents is we've got chromium. We've got chromium. We've got chromium. Chromium is a fantastic oxidizing agent. So we are not going to draw the mechanism of how chromium does this, but chromium can come in a lot of different varieties. This top one is chromium trioxide with acid. This middle one is sodium dichromate with acid. And this bottom one is chromic acid, which is an acid. So all of these are chromium under acidic conditions, good, strong oxidizing agents. Those are secondary alcohols. What about a primary alcohol? Look, it's chromium. Chromium is an oxidizing agent. It's chromium with acid. It's going to oxidize this alcohol. But this is a primary alcohol. If that primary alcohol turns into a doubly bonded oxygen, that's called an aldehyde. But an aldehyde is only temporarily observed in this reaction. Further oxidation will actually do more carbon-oxygen bond formation to form a carboxylic acid. Does a secondary alcohol form a carboxylic acid? No. Primary alcohols can form carboxylic acids. Primary alcohols form carboxylic acids when you have a strong oxidizing agent. And chromium is a strong oxidizing agent. All those previous chromium reagents, strong oxidizing agents. Yep, that says strong down there. Again, the aldehyde is observed, but only as sort of a temporary stop in the path on the way to a carboxylic acid. So anytime you use chromium, that's a strong oxidizing agent, and you over-oxidize, or at least termed over-oxidizing, the primary alcohols to a carboxylic acid. If you want to stop at an aldehyde, if you want to make an aldehyde as the product that is the final recovered product, you need special techniques. One of the special techniques is called pyridinium chlorochromate. This is the only exception to reagents that have chromium that are considered weak. This pyridinium chlorochromate, you may see drawn out like this. You may see it written slightly differently, but it's pyridine with an H and a plus, a chlorine with a minus, and a CrO3. So it's a lot like one of the strong oxidizing agents, CrO3, but this is CrO3 with acid. Acid makes the oxidizing agent strong. Pyridine, remember, pyridine is a base. and the base makes that oxidizing agent weaker. So what does it mean to be weaker? It means primary will be oxidized to an aldehyde and stop. Secondaries are always oxidized to ketones, regardless of whether your oxidizing agent is strong or weak. We're not going to draw any of the mechanisms with chromium oxidations, but we will draw this oxidation, and we will also draw the Swern oxidation. I forgot to write it on here. I will give you that reagent in a moment. The NaOCl and acetic acid, that's called the bleach oxidation. So chromium is not super safe. It's a pretty toxic reagent. Chromium-6, hexavalent chromium, that's what this is. This is chromium-6. Hexavalent chromium is carcinogenic, cancer-causing. Have you ever seen the movie Erin Brockovich? You should check it out. It's all about chromium-6. It's a real true story. So chromium stuff, toxic, not great. So we'll use it on paper a lot, but when you do oxidations in the lab, you very rarely use chromium. You're more likely to use bleach or the Swern oxidation, which is also an oxidation that does not contain chromium. Okay, on paper though, we'll use chromium. What's the difference in these two situations? This is a strong oxidizing agent. This is a weak oxidizing agent. This is AKA PCC. So in order to know how to draw these products, I need to know how to classify them. This is a primary alcohol. This is a secondary alcohol. This is a tertiary alcohol. It does not matter that these alcohols are all benzylic alcohols. We will talk more about reactions of benzene and stuff next unit, but yeah, these are primary, secondary, and tertiary alcohols, and yet they're all benzylic as well. Okay, so what? H2CrO4 is a strong oxidizing agent. That means you get a carboxylic acid when you oxidize that alcohol. It's a strong oxidizing agent. That means you get a ketone when you oxidize that alcohol. It's a strong oxidizing agent. That means that tertiary alcohol stays the same. Wait, what? Yeah, that tertiary alcohol stays the same because there is no hydrogen to lose off of this carbon. You can't make a carbon-oxygen double bond because that would explode that carbocation. Explode that carbon's octet. So tertiary alcohols cannot be oxidized. Secondaries can be oxidized to ketones. Primaries can be oxidized to aldehydes or carboxylic acids, depending on strong or weak. Tertiary alcohols cannot be oxidized. Tertiary alcohols cannot be oxidized. Yeah, leave it alone. All right. So that's what happens if it's strong. What if it's weak? Weak! The secondary still gets oxidized to a ketone, like so. The tertiary still gets left alone, like so. And the primary gets oxidized to an aldehyde, and you stop. And that's it. This is what happens. The blue is what happens when it's strong. The green is what happens when it's weak. Weak. Okay. So I said we won't draw the chromium mechanisms, but we will draw the bleach oxidation mechanism. So how does this bleach oxidation mechanism work? You start out with NaOCl, that's sodium hypochlorite. And that's an easily obtainable salt, hypochlorite, sodium hypochlorite. That sodium hypochlorite, OCl minus, attacks the H of your acetic acid solvent to yield HOCl. HOCl is hypochlorous acid. Hypochlorous acid is not a super stable acid. It's not a shelf stable acid, not something that's easy to purchase and from a chemical company and have sitting around in a bottle. So you make it in situ, which just kind of means you make it when you need it in the reaction flask. Sodium hypochlorite is the active ingredient in bleach, like regular over-the-counter bleach that you clean your shower and your laundry with. And acetic acid is a standard chemical thing. So you mix together bleach, household bleach, and acetic acid, you get sodium hypochlorite. No, you get hypochlorous acid. Hypochlorous acid is useful for oxidations. The way it starts, protonate the oxygen because it's hypochlorous acid. We protonate that oxygen to make it a better leaving group, and why I decided to put dashes and wedges on those methyls, I don't know. They're not necessary. It's not asymmetric. So protonate to make a better leaving group, and you just regenerated your hypochlorite ion. Students say, that's weird. Why do you do that? It's part of the mechanism because HOCl is not a stable acid on its own, so you have to make it. And so we show the arrows of how it's made and then the arrows of how it's used, because that's what mechanisms do. This OCl minus attacks my carbon that has my alcohol. This is an SN2 reaction. SN2. Remember, this is only happening on secondary or primary, or officially methyl, substrates, because oxidation of a tertiary alcohol cannot happen. So this step is always an SN2 to displace water and replace that water with OCl, with the OCl, hypochlorite. Okay. Then that water does a little E2-like mechanism. It's E2, but it's different from what we normally think of as E2. What we normally think of as E2 is the carbon that has the leaving group is alpha. Well, this time, alpha is the oxygen, because my leaving group is going to be my Cl. Cl is my leaving group, just like it has been in some other things. And the leaving group is always connected to the alpha carbon. So, yeah, alpha is oxygen this time instead of carbon. I'm going to take a hydrogen from the beta carbon, take a hydrogen from the beta, dump in electrons, simultaneously kicking out your leaving group. And out of that, you get, ta-da, a ketone. It always makes a carbonyl compound, but that carbonyl is a ketone if the alcohol was secondary. That carbonyl is an aldehyde if the alcohol was primary. It would also be an aldehyde if it were a methyl. It would be formaldehyde. Yeah. Okay. So this mechanism is kind of cool because it's a mixture of SN2 and E2, but it's a little bit of a non-traditional E2. It's not like the E2s we've seen before, but it's still a concerted mechanism, plucking a hydrogen, losing a leaving group, making a new pi bond. Yeah. Oxidation. How do you like it? The Swern oxidation is another weak oxidizing agent. It's going to turn this primary alcohol into an aldehyde. That aldehyde. The way it works is you have dimethyl sulfoxide, which is written that way, but dimethyl sulfoxide is a very, very common solvent. So instead of seeing it written this way, you will often see it written as DMSO. DMSO and oxalyl chloride. DMSO and oxalyl chloride are what's needed in the Swern oxidation. This is the structure of oxalyl chloride. Those two things react together in a way that we won't study until chapter 16, but DMSO and oxalyl chloride react together to make this compound. This compound has a sulfur with a positive. We're going to see some sulfurs with positives soon and very soon in this chapter. But for now, we're focusing on the alcohol bit. The way the Swern oxidation works is you attack the sulfur that's positive. Simultaneously, the chloride gets bumped out. That's like an SN2 on my sulfur. We're going to say sulfur is good at doing SN2, but it's also good at being SN2'd upon. So we attack the sulfur, kick out the chloride. There you go. In ET, that's triethylamine. Try it. You might like it. Triethylamine deprotonates, cleans up my O with a plus. and I've got this. This sulfur thingy can now be treated as a good leaving group. So triethylamine comes back to do another base thing and take a hydrogen. We have to lose a hydrogen from the carbon that has the oxygen on it. Again, this is not a traditional E2 style thing, but it's an E2 style thing nonetheless. We lose a hydrogen from the beta if we're considering oxygen our alpha, because the alpha is what has the leaving group connected. In the last example, the leaving group was chlorine. In this example, the leaving group is sulfur. So that sulfur is going to leave because we're making a new pi bond, carbon to oxygen, and we're losing one of the hydrogens on my carbon as well. So we get this aldehyde product out of those final arrows. That last little step is an E2 style thing because it's under basic conditions, under basic conditions, and you're making a new pi bond, alpha to beta. Yep. 2 oxidation mechanisms you have to know, the Swern and the bleach, but you have to recognize reagents for all of the chromium stuff as well. We're just not going through the chromium mechanism process because it's toxic and something we only ever do on paper. It's not something we do practically in the lab. That's oxidation of alcohols. All right.